This is 2.1.6 quarks and anti-quarks. I'm going to start with the three quarks that you have to know very, very well, and then I will give you the full picture afterwards. So first let's make a table where we put the up quark, down quark, and strange quark. So I already introduced the up and quark in a previous lesson, and now we're introducing another one called the strange, and then we'll put the strange in a bit more context later on. So the up quark, I'm going to write it in terms of its charge, its baryon number, and I'm going to introduce a new property called strangeness. So the up quark has a charge of plus 2/3, and this is relative. The down quark has a charge of minus 1/3, and the strange quark also has a charge of minus 1/3. So now very quickly, if we look at that in the context of a proton, you got an up, and a down. So the up is plus 2/3. The second up is another plus 2/3, so that's 4/3. Then the down is minus 1/3, that's 3/3, which is positive 1. For the neutron, you've got one up and two downs. So the up is plus 2/3. Then one down is minus 1/3, that brings it down to 1/3. And the second down, is another minus 1/3, that brings it down to 0. So it has no charge. Then the baryon number of an up quark is 1/3, because it makes 1/3 of a baryon. The down quark likewise is the same, it's 1/3 of a baryon. And the strange quark is also the same, it's 1/3 of a baryon. So all quarks are 1/3 of baryons, because baryons are made of 3 quarks. Then finally, strangeness is a property that only the strange quarks have. So up quark has 0 strangeness, down quark has 0 strangeness. And the strange quark, and it's the important bit to remember, it doesn't have a strangeness of 1, it's got a strangeness of negative 1. So the regular strange quark has a strangeness of negative 1. So these are the 3 quarks you need to know very well. But now I'm going to bring all the particles, the quarks and the leptons and the bosons, so the fundamental stuff, into a table that shows their relations and where they go. So to organize this, we're going to start with quarks. And we make a table like that. So in the quarks, we've got the up, the down, the charm, the strange, the top, and the bottom. So all of the ones on the top, they're all similar to the up quark. And all the ones on the bottom, they're all similar to the down quark. But they're heavier, more energetic as you go up. So the up quark has a charge of plus 2/3. The charm has a charge of plus 2/3. And the top has a charge of plus 2/3. The down has a charge of negative 1/3. The strange has a charge of negative 1/3. And I'm also going to write down the strangeness of the strange is negative 1. And then the bottom has a charge of negative 1/3. Then we've got the leptons. And we're going to make another similar table. So we've got the electron, the muon, and the tau. And then underneath those we've got the electron type neutrino, the mu type neutrino, and the tau type neutrino. And again, likewise, all the ones on the top are similar to each other, but they get heavier, and all the ones on the bottom are neutral. So for the electron, charge relatively is -1. The mu is also -1. The tau is also -1. And then the charges of the neutrinos are 0. And then on the side, we're going to put bosons. So here we'll put the gluon, then the virtual photon, then we'll put the Z0, and then we'll put the W plus and minus. So virtual photon has 0 charge, gluon has 0 charge, the Z0 has 0 charge, and then W plus or minus has plus or minus 1 charge, depending on which one it is. Now, going back to the particles we had last time that I put in the table. So, out of the mesons, only the kaons have strangeness. So, of the mesons, only kaons have strangeness. So the pions don't have strangeness. And then when strange particles are created, they found that there was some funny conservation going on sometimes, and then when they decay, this conservation was not happening. So strange particles, when they're created by the strong nuclear force, and when they decay via the weak nuclear force. So strange particles are created by a strong nuclear force and are created in pairs. Strange particles then decay via the weak nuclear force and then next I'm going to construct 2 diagrams that are going to help you to memorize the quark composition of all the particles. It's important to memorize these particles because it makes it easier for you to figure out how you use them in certain situations. So questions might ask you to figure out their quark compositions, but oftentimes if you don't already know them to some extent, it becomes quite difficult to actually show your method of how you figured them out or even figuring them out in the first place. Some of these particles are not explicitly stated in the specification. However, going through previous exams, they have come up in the past and they will probably come up again in the future. So, we'll start with the baryon decuplet. And here in brackets I'll put, these are the heavy baryons. So to do this one, we're going to put charge at the top and then do -1, 0, +1, +2. And then on the side, we're going to put strangeness. So we put 0, -1, -2, and -3. Then, along the values for strangeness, we'll put a horizontal dotted line. And then we'll put diagonal lines going down from the charges. Now we start from the top level. On the top level, all 4 positions are occupied. So it's 1, 2, 3, 4. On the next level, we go down to 3. That's 1, 2, 3. On the next level, we go down to 2, 1, 2, and at the bottom, we've only got 1. So let's now analyze what the quark compositions are going to be before I start adding labels onto these. So let's start with the top. Strangeness is 0. That means that at the top, all of these values will have no strange particles at all. So I'm going to leave them blank for now. On the next level, we've got -1, which means that all of these particles will have only one strange particle, and that's it. So only one strange quark. There won't be 2 stranges, and there won't be 0 stranges. So with that regard, we can pre-fill in 1 strange into all 3 of these. On the next level, strangeness is -2. So each of these needs to have 2 strange quarks. So we can fill those in straight away. And on the final level, the strangeness is -3. That means there's going to be 3 strange quarks. So we can fill in all 3. And so the bottom level is now complete. Now, on the rest of them, we still need to fill in the quarks. So on the top level, we need all 3 quarks to be filled in. On the second level, we need to fill 2 quarks in for each one. On the third level, we need to fill in 1 quark, and the bottom's already done. So the only quarks we can use now are ups and downs. So we need to figure out how can we use a combination of ups and downs in 3 quarks to make each of these charges. So to get a charge of -1, 3 downs. -1/3, -1/3, -1/3, that makes -1. So that's down, down, down. That's now complete. This is called the delta minus. The next one has 0 charge, and that sounds very familiar to us because we know that the neutron also has 0 charge and is made of ups and downs. So that one must be up, down, down. And I'll just stress the order in which you put them doesn't matter. So if I put down, up, down, or down, down, up, it's the same thing. So the order in which I put the quarks doesn't matter. That's called a delta naught. Then the next one has positive charge of 1. And again, that's familiar to us because we know the proton's quark structure. And this heavy baryon has the same quark structure as a proton. So it's 2 ups and a down. That's called a delta plus. And the last one has a charge of +2. So the only thing we can do is put 3 ups. That's +2/3, +2/3, +2/3. That makes 6/3, which is +2 charge. So this is up, up, up. And this is called a delta plus plus. Now, we can do this for the rest of them to figure them out. But there's also another way, a faster way of doing it, is on the previous page, I showed you in the tables the up-type quarks, which are the up, the charm, and the top, and the down-type quarks, which are the down, the strange, and the bottom. So, if we follow these charges along, where there is a down-type quark, there will be another down-type quark, where one of them is already filled in with a strange. and then the other two will just follow along. So the first down is a strange, and the missing ones can't be strange, but they have to be down types. So 2 downs. Likewise here, you got 2 downs. One of the downs is a strange. So we're going to have one more down and one up. So that's S, D, U. And then over here, you've got 1 down, which is a strange, because strange is a down type, and then 2 up. So that's S, U, U. And these are called the sigma minus, the sigma naught, and the sigma plus. Another particle also has the same quark composition as a sigma naught, which is called the lambda naught. It's a capital lambda. So they have the same quark structure. Okay, going on to the next one. So, again, along this line, we've got 3 down types. 2 stranges are already a down type, so the last one is also a down type. So that's SSD. Then on the next one, it's 2 down types and an up type. So SS are 2 down types already, so it's SSU. And these are the cascade minus and the cascade naught. And then the last one that's already filled in with the 3 stranges, that's called the omega minus. Now, if you want the anti-quarks of these, all you simply do is anti-everything. So if you anti-everything, all the negative charges, they become positive. All the positive charges become negative. All the quarks become anti of the quarks you see in there. The strangeness on the side becomes anti, so they become positive. So an anti-strange particle has +1 strangeness. Then we'll do the meson octet. So we'll do something similar. We'll do charge -1, 0, +1. And then we'll do strangeness. Now the meson octet is slightly different to the baryon decuplet, where we can not only have negative strangeness, but we can also have positive strangeness, because we're made of quark-anti-quark pairs rather than 3 quarks. Whereas if you're made of 3 quarks, it's impossible to have a positive strangeness, because the regular strange quark, not the anti, doesn't have positive strangeness. So we'll do 0, +1, -1. So for the meson octet, we fill in the center first with 3, so all 3 are occupied. Then to decide what side we can occupy on the top and the bottom, we have to think about the strangeness and the charges. So, for example, at the top we have a strangeness of +1. That means that everything along the top must have an anti-strange quark involved. Now, if they have an anti-strange quark involved, the charge of an anti-strange is +1/3. And if you've got +1/3, then the only way that you're going to make charges with a normal quark, because the second has to be a normal quark now. If the anti-strange is the anti-quark, the second one has to be a normal quark. So the only normal quarks we have available are the up and the down. So if we do an anti-strange and a down, that will give us 0 charge. And if we do anti-strange and an up, that will give us a positive charge. So that -1 at the top can't be used. But these two can. Then at the bottom we do the same thing. The bottom has strangeness of -1, so the regular quark is a strange, because that's a strange. And strange is regular quark. So the second quark must be an anti-quark, which can be an anti-up or an anti-down. So if you've got a strange of -1/3 charge, if we put an anti-up, this will be -1 charge. If we put a down anti-down, sorry, then it's going to be zero charge. So we can't have a positive charge on the bottom. So we fill that in. Now, it's easiest to start from the middle because we don't need to worry about strange at all. So if we start right in the middle, to get a strangeness of 0 and a charge of 0, we need to have an up, an anti-up, or a down and an anti-down. So up, anti-up, or down, anti-down. And these are the pi naughts. So two versions of the pi naught. Then, for a positive charge, we need an up and an anti-down. That's the pi plus. For the negative charge, we need a down and an anti-up. And that's the pi minus. Notice, it's always one quark, one antiquark. The mesons are always one quark, one antiquark. There cannot be two quarks, there cannot be two antiquarks. Then, at the bottom, we know that we're going to have strange in both of them. So now we have to put an antiparticle in each of these. So to get a negative charge, we do strange and anti-up. That gives us a negative charge. That is a K minus. Then over here we've got strange. So to get a zero charge, we have to put an anti-down. And I'm going to hold off on writing what K that is for now. I'm going to come back to that one. At the top here, it's got a strange of +1. So both of these must have an anti-strange quark. So the other quark has to be a quark, not an antiquark. So from anti-strange, to get zero charge, we need a down. And then, for the plus charge, it's an anti-strange and an up. So this one will be a K plus, a positive K-on. Now the two I've left blank are going to be neutral K-ons. However, one of them is the regular neutral K-on, and one of them we call the anti-neutral K-on. So to determine which one is which, we actually look at the non-strange quark. If the non-strange quark is a regular quark, then that's the K naught. And if the non-strange quark is anti, then that's the anti-K naught. So this is the K naught, and this is the anti-K naught. Yeah.
How do they get into pies if the pies start streams?
We're actually going to do that in 2.1.7. So I'll come back to your question in 5 minutes in the next video. Okay, that's the end of 2.1.6.